Okay, let's move on to section 2.3 of Anton, which is the properties of determinants and Cramer's rule. So if A and B are n by n matrices, then an important and maybe surprising fact is that the determinant of their product is the determinant of A times the determinant of B. So remember, the determinant of an n by n matrix is a number. So this is a number, this is the number, and it's saying when you multiply these two numbers, you get the same result as the number on the left-hand side here, which is the same as, which is the number that arises from taking the product of these two matrices. So A times B is another n by n matrix. It's determined to some number. And this is a very surprising fact from the perspective of the way we've introduced determinants as some complicated formula involving expansion along a row or a column. So to explain a little bit about where this formula comes from is what the next few minutes will do. But first, let's say that a fact that's not true, and that's why I've crossed it out over here, is that the determinant of A plus B is not the determinant of A plus the determinant of B. Okay, so to explain this fact here, we have to go to talking about elementary matrices again. This is something we've covered in chapter 1. So first of all, there's 3 general types of elementary matrices, and you get those by starting with the identity matrix, the n by n identity matrix. Here I have a 2 by 2 identity matrix, and then doing a single row operation. And then there were 3 types of row operations. One, I guess the first one here is multiplying a row by a scalar. So I've multiplied row 1 by the scalar 2, and that's how I got this elementary matrix here. Or I could get this matrix, which I get by starting with the identity matrix and replacing row 1 by adding to it 2 times row 2. 2 times row 2 is 0, 2. Adding that to 1, 0, I get 1, 2. I keep row 2 the same. It's only row 1 that I've replaced by adding to it 2 times row 2. Okay, and then an example of the third type of elementary matrix is where I swap 2 rows. Here in the 2 by 2 case, there's only 2 rows to consider, and so when I swap them, I get this identity matrix, this elementary matrix. And the point of these elementary matrices is that when you multiply on the left any matrix by any particular elementary matrix, the corresponding operation, or the result I should say, is the same as applying that corresponding elementary matrix operation to that matrix that you're multiplying. So if we start with a matrix B and multiply it on the left with the associated elementary matrix, what we'll get is the result of applying the elementary row operation that gave rise to E, applying that to B. And a fact we've seen last time is that the determinant of the matrix you get when forming or applying a row operation to E times B is the original matrix, the original determinant of the original matrix B. But sometimes the determinant changes by the determinant of E, or gets multiplied by the determinant of E. For example, when you swap 2 rows, the determinant gets multiplied by -1. When you multiply through a row by a certain scalar, the determinant of your new matrix gets multiplied by that scalar. And then when you when you replace a row by adding to it a multiple of another row, the determinant does not change. And so the determinant of this matrix here you see is 1, and that's consistent with the fact that when you do an elementary row operation corresponding to replacing row 1 by adding to it 2 times row 2, the determinant doesn't change. Okay, let's move on to a theorem that we can prove using this fact here. So that theorem says that if A is a square matrix, then A is invertible. Remember, that means that there exists some matrix B, so that A times B is the identity and B times A is the identity. That matrix A is invertible if and only if the determinant is non-zero. So this is an important theorem because it allows a quick criteria to determine whether a matrix is invertible or not. You just have to ask, is the determinant equal to 0 or not? This theorem is used very frequently. Okay, so what's the proof? Well, we go back to chapter 1 and talk about doing the elementary row operations to this matrix A. Again, doing elementary row operations corresponding to multiplying on the left by the associated elementary matrices. And then once we get to reduced row echelon form, we'll get, with this matrix R. And if A is invertible, then the reduced row echelon form is the identity matrix. And so we get this equation here. This fact here that I've asserted, it takes a little bit of thought, and so if that's a little, if you feel a little unsure about that, that's okay. Just accept it for now. Okay, and so then what we know is that the determinant of when you multiply by an elementary matrix, the determinant also multiply. And so we have, by taking the determinant of both sides of the equation here, we get that the determinant on the left-hand side here equals the determinant of I, and the determinant of the n by n identity matrix is just 1. So again, I here is the n by n identity matrix that just has 1s along the diagonal, 0s elsewhere. And so its determinant is 1, and then we've got all these things here, and the determinant of any elementary matrix is non-zero, and so therefore that forces the determinant of A to be non-zero, because you can't have, if it was 0, then this left-hand side would be 0, but the right-hand side would be 1. Okay, so that proves one direction, that if A is invertible, then the determinant is non-zero. The other direction of the theorem is, well, if A is not invertible, we have to show its determinant is equal to 0. And once again, the proof is to go back to the equation where the product of a bunch of elementary matrices times A is equal to R. But in this case, the case where A is not invertible, R will have a row of zeros. Again, R is a reduced row echelon form. And so here's a 3 by 3 example. You'll have a row of zeros, and its determinant of R will be 0, because when you expand by minors along this row, you'll get the determinant of R is 0. And then once again, that forces, because the determinant of all these elementary matrices is non-zero, but the determinant of R is 0, that forces the determinant of A to equal 0. Again, if A is not invertible. Okay, so now we're going back to trying to prove that the determinant of A times B equals the determinant of A times the determinant of B. And we need some smaller results. Mathematicians tend to call these lemmas to approach the proof of the main theorem we're trying to establish. So this lemma is that the inverse of an elementary matrix is an elementary matrix. And the reason is quite simple, actually. It's that each elementary row operation is reversible by a process that itself is an elementary row operation. So here I've done the 3 cases. So if the elementary matrix you started with just swaps row I and row j, then if you swap them again, you get back to the original matrix. And here's an illustration. So if E is the elementary matrix corresponding to this elementary row operation of swapping rows I and j. Now here I've only done the 2x2 case, but the general case is similar. Then the inverse is the same operation, so the same matrix. So E is its own inverse in this case. All right, and this again is an elementary matrix. I mean, it's the same one as here. Now, one of the other types of elementary row operations is you take row I and multiply it by a non-zero scalar. So if that's the elementary matrix you start with, here's an example where we take the first row of the identity matrix and multiply through by 2. Then to get the inverse, what you would do is multiply that same row by 1 over s, where s is the scalar you originally multiplied row I by. So if we multiply it through by 2, we multiply that same row by 1/2, and that's the inverse. That will give rise to the inverse matrix. And if you multiply E and this matrix, you'll get the identity matrix. And again, this is just a 2x2 case, but the n by n case is similar. And then finally, if the elementary matrix you started off with is formed by taking row I and replacing it by adding to it a multiple s of row j, then you can get back to the original matrix by taking our new row I and adding to it negative s times row j. Basically, you're just subtracting off the part you previously added, and that will give you your original matrix. So if E is this elementary matrix that's formed by taking the identity matrix and adding to row 1 2 times row 2, then the inverse matrix is we take row 1 and add negative 2 times row 2. And that's this. And if you multiply these two matrices, you indeed get the identity matrix. Okay, so that proves this lemma here, that the inverse of an elementary matrix is an elementary matrix. All these matrices are elementary matrices. The next lemma we'll need is that every invertible matrix can be written as a product of elementary matrices. And to prove this, we once again start with the equation here that we get by starting with our invertible matrix A and row reducing it. And when we get to reduced row echelon form, we'll end up with the identity matrix. Okay, so once we have this equation, we multiply both sides of it by the inverse of ER. ER is some elementary matrix. We multiply by its inverse. And on the left, ER inverse and ER, they multiply to get the identity matrix, so it disappears. And then we get E sub r minus 1 times E sub r minus 2, all the way to A, is equal to E sub r inverse. And then just repeating the same process of essentially canceling or multiplying by the inverse of E sub r minus 1, we get this equation here, and then just continuing that process, we get that A is the product of these inverses. These are the inverses of elementary matrices, and then the lemma we just proved above says each of these inverses is an elementary matrix itself, and so now we've expressed our original matrix A as a product of elementary matrices, which is what we're trying to show. Okay, so finally we can now move on to the main theorem we're trying to prove, which was this amazing fact that the determinant of A times B is equal to the determinant of A times the determinant of B. And in this proof, I'm going to assume that we know that the determinant of an elementary matrix E times any matrix M is the determinant of E times the determinant of M. We've seen that asserted a few lectures ago, or anyway. So, okay, if A is not invertible, then it's actually relatively easy, because then we know that the determinant of A is 0, so this side is 0, and then A times B is also not invertible. That might take a little bit of thought, but let's just assume that. And so then the determinant of AB is 0, again by the result we proved a few minutes ago, actually. And so both sides of this equation here are 0, so that case is easy. The little bit more involved case is A is if A is invertible. And here's where these lemmas that we proved came in. Write A as a product of elementary matrices. Now on the previous slide I had written A is equal to E1 inverse. Here I've just relabeled things and have written A as a product of elementary matrices. Okay, so then I'm trying to show this equation up here. So I start with the left-hand side, determinant of A times B. Well, that's equal to determinant of, now I replace A by the product of these elementary matrices, and this B is just there. And by this fact here, that I can move, or basically I know this result when A is an elementary matrix. So since E1 is an elementary matrix, the determinants behave like so. And then continuing to E2, I can move the E2 out of this product and take its determinant, and so on. And then finally, till I get to this step here. And then now I combine the determinant of E1 and the determinant of E2. That their product is the determinant of E1 times E2. That's again this result here, that as long as one of the matrices is an elementary matrix, I know that the determinant is multiplicative. And then continuing again, and so on, I get the determinant of the product of the EIs, and the product of the EIs was A, and so we get determinant of A is equal to determinant of